Have you ever stopped to wonder how your phone streams a perfect video with no lag? Or how your headphones can just create this little bubble of silence on a noisy train? Well, it's not magic. It's actually a single, incredibly powerful mathematical idea. Today, we're going to decode that hidden language that shapes our entire digital world, information theory.
So let's start with a bit of a riddle. What on earth could possibly connect your noise-canceling headphones, the signal strength on your phone, and even your doctor's medical records? Well, the answer is a totally revolutionary theory that took this fuzzy, abstract concept of information and turned it into something real, something we can actually measure, manipulate, and ultimately master.
And that's where we're going to kick things off by exploring how this amazing theory managed to turn something as simple as a message into pure, predictable mathematics.
You know, this quest to measure information actually started way before computers were a thing. Back in the 1920s, engineers like Nyquist and Hartley were already wrestling with how to compare different telegraph systems. But the real game changer came in 1948 when a brilliant mathematician named Claude Shannon published a theory that would become the absolute bedrock of our digital world.
So what is information theory, really? Well, at its heart, it's this radical idea that we can assign a precise number to the amount of information we get when we learn something new. It's a way to measure the unmeasurable, turning everything from a text message to a radio wave into pure, hard data. Okay, so that leads to a pretty interesting question. If we can measure information, what are the units? Well, the answer is the bit, and it's tied to an idea that you might not expect at all, the science of surprise.
And this is where it gets really cool. Think about a super predictable message, like, say, a string of the letter A. You know exactly what's coming next. It's kind of boring, it's redundant, and it has very little new information. But now think about a totally unpredictable message, like, they arrive at dawn. Whoa, every single word is a surprise. And that surprise is the key. The more surprising and unpredictable a message is, the more information it actually contains. Shannon captured this whole idea in his famous formula for entropy, which you can see here labeled with an H. Now, don't worry, you don't need to solve the equation to get the big idea. This is just the tool that lets us put a number on the average amount of surprise, and therefore, the average amount of information in any message out there.
So what does that mean in the real world? Well, Shannon figured out that the entropy of written English is only about 1 bit per letter. Now, think about this. If every letter in the alphabet was equally likely, it would take almost 5 bits to represent each one. This just shows you how much redundancy is baked into our language. It turns out we are surprisingly predictable creatures. Okay, so we can measure information. So what? How does that actually help us build things? Well, let's move on and see how this very theory allows complex systems to literally learn from their environment. So how do we put this theory to use? One of the most powerful ways is in building what we call adaptive systems. These are systems that don't just follow a fixed set of instructions, they actively change and get better by interacting with the world around them. Simply put, they are systems that are literally designed to learn. So how does a system actually learn? Well, it uses this clever little thing called a feedback loop. First, it produces some kind of output. Then, and this is the magic part, it compares that output to a reference signal, which is basically what the correct outcome should have been. The difference between the two? That's the error signal. And that error signal gets fed right back into the system, telling it exactly how to adjust for the next attempt. It's this continuous cycle of trial, error, and getting a little bit better each time. We can actually break that whole loop down into 4 simple steps. 1, the system generates a signal. 2, it compares that signal to a reference of what's correct. 3, it finds the error, or the gap between them. And 4, it uses that error to tweak its own settings, and then it just tries again. That's it. That is learning, boiled down to an algorithm. So where do you see this stuff? Oh, it's everywhere. This is the tech that cuts through the noise in sensitive equipment, that cleans up distorted signals for your phone calls, and, bringing it right back to our first question, it's the secret sauce that powers the active noise control in your headphones, constantly adapting to the sounds around you to create that sweet, sweet silence. All right, so if a simple adaptive system can learn to cancel noise, just imagine what a massive, interconnected system could do. And that brings us to one of the biggest information challenges of our lifetime, totally revolutionizing the medical record. For years and years, your medical history was just scattered all over the place. A file here, a folder there, all organized around different doctors and hospitals. The big goal now is to completely flip that model on its head, creating one integrated system that revolves around you, the patient. And this isn't just about scanning paper, it is a fundamental problem of information flow.
And the difference is just night and day, right? We're moving away from these siloed, static, error-prone paper records and into a future of integrated, dynamic, electronic medical records, or EMRs, that can be accessed securely, anywhere, anytime.
But actually making this happen is incredibly difficult. The single biggest hurdle is something called interoperability, and it really comes in two flavors. You've got technical interoperability, which is just about getting different computer systems to physically talk to each other. But the much harder part is semantic interoperability, making sure that when data moves from one system to another, its meaning is perfectly preserved. You have to make sure the vital signal of your health isn't lost in the noise of translation.
And because we're talking about our most sensitive personal data, trust is everything. To build a secure EMR network, you need these 5 essential keys. First, you need authentication, proving you are who you say you are. Second, authorization, making sure you only see the info you're actually allowed to see. Third, access logging, a digital paper trail of who saw what and when. Fourth is encrypted transfer, scrambling the data so it's useless if someone intercepts it. And finally, auditing, constant checks to make sure everybody is playing by the rules.
So you see, whether it's that tiny little feedback loop in your headphones or the massive, sprawling network of a national healthcare system, the challenge is always the same. How do you manage information effectively? And this brings us right back to the other pillar of Shannon's incredible theory.
This right here is the other giant pillar of information theory, Shannon's channel capacity formula. If entropy tells us how much information is in a message, this formula tells us the absolute, unbreakable speed limit for sending that information reliably through any channel, like a wire or the air itself, that has any amount of noise.
And what is so powerful about this is that it shows us the exact trade-offs we have to make. To send data faster, you've really got two options. You can get a wider pipe, that's the bandwidth, W, or you can shout louder than the crowd, which is increasing your signal power, S, relative to the noise, N. Every single communication system ever built is just a different way of balancing these three things.
And the impact of knowing this universal speed limit? It is absolutely staggering. It's the theoretical foundation for our faster internet, our clearer phone calls, our ability to talk to probes in deep space, and even the spread spectrum technology that lets tons of us share the same channel without getting in each other's way.
And really, that's the main takeaway here. From the clever little adaptive algorithm in your headphones to the vast architecture of our national healthcare data, it all comes back to these same foundational principles. Information theory isn't just some abstract idea. It's the invisible blueprint of our modern world.
Which leaves us with one final question to think about. We are creating data at an absolutely explosive, unbelievable rate. Shannon gave us the mathematical tools to measure it and to transmit it. So, as we look to the future, what do you think is the next great information challenge that we're all going to have to solve?